It's an honor to have Thomas Sandholm here today from CMU. Thomas is professor of computer science at CMU. He did his PhD work. This is odd. I hear myself booming in my ears, but I'll say it louder. So he did his PhD work at University of Massachusetts at Amherst, and then did a brief tour at Washington University, and then on to professorship at CMU. Among Thomas's many honors are the Ijkai Computers and Thought Award, the inaugural ACM Autonomous Agents Research Award, the Alan Newell Award for Research Excellence at CMU, the Sloan Fellowship, the Carnegie Science Center Award for Excellence, Edelman Laureateship, and the NSF Career Award. And he's a fellow of ACM, AAAI, and Informs. He's not really old enough to hold any honorary degrees, but he holds an honorary doctorate from the University of Zurich. How'd that happen? That's interesting.
They made a mistake.
Okay. Now, if you watch we just did our fireside chat interview, and if you watch that, this is an attractor. We talk about Thomas's famed history as a windsurfing champion, including winning the champion windsurfership in Finland in 1986, I think it was. But he's a long history of being a sports person. And even playing under the emblem of the Finnish Air Force as a windsurfer. That's one way you get out of service. You just windsurf your way through your service in the military. Whenever I look at Thomas, when I see Thomas show up in a little sport coat like this, a nice sport coat, I think about a really wonderful experience we had when Thomas visited us. It must have been like 1999 or something. 98. And we went on Jack Breeze's boat for dinner across the lake on a beautiful day. And about halfway across the lake towards, I think it was Daniel's Broiler, it started absolutely pouring out. And we were kind of all dressed in windbreakers, but Thomas looked exactly like this. In the pouring rain, standing in front of the boat, and came in looking quite dapper, but we all knew that his clothes was kind of a different shade when he walked in to sit down for dinner in this soaking wet sport coat. With that little story and vignette, Thomas will talk about superhuman AI for strategic reasoning. Thomas.
Okay. Well, thanks a lot for having me again. It's great to be here. I seem to come here every few years. Can you hear me okay in the back? All right, great. So I'm going to talk about superhuman AI for strategic reasoning, and mostly I'm going to talk about Libratus and the techniques that went into it, which we recently published in Science with my PhD student Noam Brown. And then in the end, I'm going to talk about some of the other things that are going on, these topics in my lab and applications and so on. All right. And by the way, do ask questions along the way. So imperfect information games are very unlike chess or Go, where in chess or Go, you know exactly what the state of the world is. In imperfect information games, you don't. They're much more like negotiation or poker or military settings or video games and so forth. So you all have probably heard about AlphaGo and AlphaZero, and it's a great success story in a very complex game. And those techniques can, in principle, apply to other perfect information games. And in fact, they have shown very good success, for example, in chess and shogi and so on. However, they don't apply to imperfect information games at all. So in perfect information games, you can solve a subgame of the game tree based on information in the subgame alone. So for example, in chess, how you play the Sicilian defense is completely independent how you should play the Queen's Gambit. This is not true in imperfect information games. And to highlight this difference, let me run through an example. And this is a small example we call coin toss. This also shows the general representation. How do you represent imperfect information games in a game-independent way? This is called the extensive form, which is a standard representation in game theory. All right, so how this works, this example, and by the way, this is a tiny game just for illustrative purposes. The real games are huge. So we have 3 players. There's chance, but player 1 and player 2. Chance really just acts stochastically, not strategically. And let's say in this game, chance just flips a coin, heads or tails, 50-50. Then player 1 can either sell the coin or play. And if player 1 plays, then player 2 gets a move, gets to guess which way the coin came out. Heads, tails, or player 2 can just give up and say, well, I don't know, you win. The payoffs are shown from player 1's perspective. Player 2's payoff is just the negative of that. So if player 2 guesses correctly, player 1 gets -1. And if player 2 guesses incorrectly or forfeits, player 1 gets 1. Okay? Now, unlike perfect information games, there's this extra structure here called the information set, oftentimes noted by this dashed line or this purple ellipse. That just represents the fact that when player 2 has his turn to move, he doesn't know whether he's in the left blue node or the right blue node. He has to infer that information from player 1's strategy, which player 2 doesn't know. Okay? So what is rational play here? Well, I've shown one Nash equilibrium of the game here. A Nash equilibrium in general is a profile of strategies, one strategy for each player, where no player can improve their expected utility by deviating to a different strategy. And what's a strategy? Well, it's just a mapping from information sets to action probabilities at that information set. And an epsilon Nash equilibrium is a strategy profile where no player can improve more than epsilon in expectation. And note that in Nash equilibrium, the beliefs are derived on the fly as we go down the game from the equilibrium and the observations so far using Bayes' rule. So this is, in some sense, game theory is a generalization of Bayesian reasoning, and it's a generalization of MDPs. So this is really a generalization of POMDPs into a multi-agent setting. All right, so one equilibrium here is where player 1 goes 50-50 sell and play. By the way, here I'm now assuming that the sell option is worth 0. So you can throw away the coin. You don't get anything for it, and you don't have to pay to get rid of it. And here 50-50, and player 2 guesses heads half of the time and tails half of the time. All right? This is not the only equilibrium. Turns out that there's an uncountable number of equilibria even in this simple game. Okay, now to make my point, I'm going to argue that this subgame here in this purple rectangle can't be solved with information from the subgame only. So if this were a complete information game or perfect information game, this could be. And most of the algorithms like minimax search, alpha, beta pruning, and so on, they are based on the idea that you can solve the subgame and do solve the subgame based on information only in the subgame. This can't be done here. So now, first I'm going to say that the payoffs for selling are 2 and -2 respectively. In that world, what would player 1 do?
Sell with heads.
Sell with heads, yes, and
Play with tails.
play with tails. That's right. So when player 2 gets a move, player 2 knows that it's tails. So player 2 can get tails, guess tails, and win whenever it was tails. Now, if I flip the payoffs in these triangles now, you'd get the opposite. And player 2 should guess heads whenever he gets a turn. So that just proves that how player 2 should play depends on information that's outside of the subgame, namely in these triangles. And here it's a simple example. Those triangles could be arbitrarily big and have transfer effects in the game from very far away. Try to remember this game because I'm going to use this as a running example later on. Any questions on the game itself? Okay. So when we tackle imperfect information games, we can't use techniques for perfect information games. We develop application-independent techniques. So these are not poker techniques. And also they're algorithmically creating the strategies. So we're not programming the strategies by hand or anything like that. Challenges here, well, uncertainty about what others and chance will do, but more importantly, uncertainty about what others and chance have already done. That gives me hidden state. And then I have to think about what do my actions signal to my opponents about my private information? And what do my opponent's actions signal to me about the opponent's private information? The really cool thing here is that we don't have to assume a meaning for the signals. That automatically falls out of the classic solution concepts in game theory like Nash equilibrium and its refinements. So the real work here is to marry those classical solution concepts with algorithms so we can compute something that's near a Nash equilibrium. So poker itself, that has been a recognized challenge problem in game theory, OR, and AI for decades. And if you actually go back to John Nash's PhD thesis, which actually was very short and you should, where he introduced Nash equilibrium, which really transformed all of economics and many other sciences, the one and only example there was poker. So, but that was a poker game called Coon Poker, which has 3 cards in the deck and only 1 card in each of the 2 players' hands. So it's a very small form of poker, so small that you can actually solve it by hand, paper and pen. And then there's been steady progress in poker, but really there's been tremendous explosion in work on using poker as a benchmark over the last 14 years. And hundreds of papers, I'm not going to try to do a full literature review. I'm going to just mention kind of 3 highlights here. One is Rhode Island Hold'em. This is a game that has 3 billion nodes in the game tree, and we were able to solve it exactly in 2005. So this was about 4 or 5 orders of magnitude bigger than what had been solved before. And the key idea here was lossless abstraction. So you can actually algorithmically walk through the game tree, get rid of 99% of it roughly, and you get a game which you solve, and then you get an exact answer to the original game. So in some sense, there are so many weird isomorphisms in these games that you can get rid of all of them and still get an exact solution, although you're solving a game that's only 1/100th of the size. And then with C-Plex's LP solver, in 25 days on a small supercomputer, we were able to solve that abstracted game to get an answer. Then the annual computer poker competition started in 2006, where different teams around the world compete on the same benchmarks, and you can measure progress year to year and group to group, and that has really fueled progress in the field because most of the top teams have been publishing their results and building on each other's work. Then Limit Texas Hold'em was near optimally solved by Bowling et al. In 2015. That's another science paper. And that's a game that has, after lossless abstraction, 10 to the 13 information sets, 10 to the 13 decision points. And this was the heads-up variant, which is 2-player. And limit means that whenever it's your turn to move, if you bet, there's a fixed amount you can bet. There's no choice as to how much you bet. And that means that the branching factor is 2 or 3, depending on the situation. Now, heads up, no limit Texas Hold'em is a whole other animal. This has become the main benchmark and challenge problem in AI for imperfect information game solving. It has 10 to the power of 161 different situations a player can face, information sets. And for this audience, I probably don't need to explain what that number means, but it's more than the number of atoms in the universe. And even if you had a whole other universe for every atom in the universe and counted those, it's more than that. So you're not about to store this anywhere, and you're not about to traverse this game tree even once. So you need some totally different techniques. This is mostly played on the internet, but it's also played on TV and in the top poker movies. Many people consider this a purist form of poker because it's really 2 players, so there are no 3rd players or 4th players that are going to mess it up. It's really, am I better or is Max better? Just like chess. And no prior AI has beaten top humans at this game. All right. So how many of you actually know this game? Okay, so not everybody. So I'm going to walk through this a little bit to the extent you need to know how the rules work, just on one slide. So first, chance deals 2 cards in private to each player, both players. Then there's a round of betting. Then chance deals 3 shared cards face up on the table. Then there's another round of betting. Then chance deals 1 shared card face up on the table. Then there's a round of betting. Then there's a 4th round where chance deals 1 more shared card on the table and a round of betting. All right, so at this point what we have, the player is holding 2 cards in private and 5 public cards on the table. What you try to do is make the best 5-card hand out of those 7 cards. And whoever has the better 5-card hand wins the whole pot. The hard part is the betting. So you have to decide whether to bet or not, and if the opponent has bet, whether to call, fold, or bet even more, which is called raising. If somebody folds, they lose the pot right there. And only if both players come all the way to the end do you actually compare the hands. So that's how it works. And when I say 10 to the 161, I mean one play of the game, just as shown on the slide. So when we play, let's say, 120,000 repetitions, it's not counting the repetitions. Just one hand of poker is 10 to the 161. Any questions so far? Yeah.
How does bluffing get factored into this?
Well, let me answer that at the end if that's still unclear. Okay. So in January 2017, I organized this Brains versus AI rematch. And I'm calling it a rematch because I had organized a similar match in April 2015 where we took on 4 of the top humans at this game and we couldn't beat them. It's very close. Statistically speaking, it was actually statistically insignificant, so a statistical tie, but we couldn't beat them and they ended up ahead. So now we had this new AI called Libratus. It's Latin stands for balanced, for Nash equilibrium, and powerful for its forceful play style. That took a while to figure out that Latin name. Anyway, so we played against 4 of the best heads-up Nolan Texas Hold'em specialist pros. So these are professionals not just at poker, but at this particular form of poker. And it's very important because, these guys are way stronger than the typical general TV pros that you might see at this particular kind of poker, which is 2-player. We played 120,000 hands over 20 days in January 2017. So each one of them played 30,000 hands. And it's important that you play a lot of hands for 2 reasons. One, you don't want this to be decided by luck. You want it to be statistically significant. And in 2015, we played 80,000 hands, and it was not enough to get 95% statistical significance, which is the threshold we use in the annual computer poker competition. So now, my worry was that if we were a little bit behind, or even a lot behind the humans back then, now humans had probably progressed a little bit, but hopefully we had progressed more, so it should have been even closer. So I felt that we would need even more hands to get statistical significance. And it would have been kind of a shame to have another event where we can't really declare a winner. The other reason is that you want to give the humans the best possible chance to find weaknesses in the AI and exploit those weaknesses. So like you may have heard about the Dota 2 bots, which are able to beat top humans for a while, and then when humans get to play with them more, even average humans can beat them. So that you want to make sure that this is not just some sort of a transient, that for a while you can beat them when they don't really know your holes. I'll come back to that.
Question?
Yeah.
How many hours a day are they playing to get to?
They got to choose all of the parameters. I actually have a whole slide. We can talk about that in the Q&A part. But they chose 20 days. We said, okay, how many days do you want to play over? This was a given. But everything else they chose. How many days, when to take breaks, break days, hours of the day. They got to choose, even dynamically. Like on one day they said, oh man, one of our players feels really tired. Maybe they're getting a cold. Let them not play. So we said, okay, yeah, this afternoon we don't play. And so on. So what it ended up being on average, maybe excluding breaks, maybe about 8 hours a day. With breaks, maybe 10 hours a day, which is way less than what they normally play. So sometimes these guys play like 3 days straight. Yeah.
Did you pair the random number generator for chance, maybe to get higher statistical significance?
I'll come to that. And we did a conservative experiment design where we let them pick almost all of the parameters of the tournament, so we wouldn't get to the kind of a Kasparov-like whining thing at the end in case we would win. I have a slide on all of those parameters if you're interested in that.
Does the AI use information over its games with the pros?
I'll come to that.
Okay.
How the AI works. First I'll talk about the match and then I'll talk about how the AI works.
You need a big queue of questions hovering here.
Yes, most of which I'm skipping, so it's great to take questions if you don't have to answer them. So this is what it looks like. So here we have my PhD student Noam, some of the casino personnel. Here's our dean looking very worried. He told me up front that if you don't win this time, you're fired. I hope he was joking. I didn't want to test him. And here's Jason Less, one of the pros, and here's Daniel McCauley, one of the pros. But you see only two of the pros here. Where are the other two? So this is a casino floor. These guys are playing in public. The other two are playing in a private isolation chamber on the second floor, where, per your question, we're actually doing duplicate matches. So whatever hand Daniel gets against the AI, he's paired human. In that match, the AI gets that against the human. So neither the humans nor the AI can systematically get lucky because they're essentially getting the same hands. And of course, you have to keep them in isolation, otherwise they could tell each other what hands are coming next. And yeah, all right. So we're having some fun with Jason. This is what it looks like. They actually chose to play two tables at once. So a left table, right table. And so these are different hands. And they can choose to play like 1, 1, 1, 1, or play all of the hands of a session here and then here. But they like to do this because they're used to playing multi-table. And they can then let their brains stew on some of the tough questions on one table while making progress on the other table. So this is one of the parameters that they selected. Here you have a chat window which they could choose individually whether to keep on or not. So whether the audience could actually interact with them. And Jason loved it. He felt that he plays best when the audience is cheering him on and for mankind. And some of the other humans felt that, no, I'm going to turn it off. I want to just focus, and I'm best when I'm just focusing.
So do people stew on questions, and they do time share? They go back and forth.
Yeah.
Is there a kind of a typical responsiveness people have, or do they actually stew for a while?
It depends on the hand. So most hands are very easy to play. So most hands, they just know how to play optimally very quickly. And then there are some difficult hands where they take more time. We had no time limit for the humans. So actually, the timing was interesting. We got a lot of angry comments on the chat saying, oh, the bot thinks too long. Well, turns out that on average, the humans thought 20 seconds, the bot thought 13. So the bot was actually playing faster than the humans. But its thinking behavior was very different. So first of all, the AI didn't think at all in the first two betting rounds. It's basically using a lookup table. And then it would tank. It would stop to think for 30 or 45 seconds in the beginning of the third betting round, which is a very unusual timing for the humans. So they kind of got disoriented with that. And the audience. The other thing is that humans generally think harder when there's a lot at stake. So if there's a lot of money in the pot, the humans think harder than if there's a little bit of money. The AI does the exact opposite, because the less money there is in the pot, the more re-raise possibilities there are, and the bigger the game tree after that is. So the AI would actually think the longest when there was the least at stake, which was weird for the audience as well. Yeah.
So all of the game work assumes that humans are perfectly rational, as they are as powerful as the machine in terms of solving these trees. Do you think these guys are closer to those assumptions, and what happens if those assumptions are not?
Good. So what if the opponent isn't rational? Well, there's a whole other line of work that has been done in the field and to which we've contributed also, called opponent exploitation, trying to exploit weaknesses in the opponent. But I'm going to talk about why I decided not to turn those things on here, because this Nash equilibrium approach is safe. If the opponent does something that's not rational, it can actually only help me, because it's a zero-sum game. So we wanted to build an unbeatable AI. We didn't necessarily want to exploit the humans by the biggest possible amount. Well, now we're going so many questions. Let me postpone, because we have a lot to cover. Okay. So up before we go to the bottom line there. So people really believe in people. So the international betting sites put us as a 4-1 or 5-1 underdog on the morning of the event. So we were walking into this as a huge underdog. But what happened is this. Libratus beat the top humans in this game by a lot. Statistical significance 99.98% or a p-value of 0.0002. Or if you like, finance 4 sigma. It's a very clear victory. So my worry that, okay, maybe 120,000 hands wouldn't be enough was totally unfounded. We had just blown past the best humans in the 18 months between the previous match and this match. The win rate was 147 millibig blinds per game or 14.7 big blinds per 100 if you're a poker player. Each of the humans individually also lost to Libratus, and this was kind of a big deal. So now, before we go to the techniques, then I got an email from China saying, okay, well, that was fantastic. Now we're in April 2017. That was fantastic. I want you to come and do the same thing in China. And I'm like, well, there's no value to it. We've already beaten the best humans in the world, so there's no scientific values. So I don't really think so. And he said that, well, actually, you know, he was actually one of our PhD graduates, a very famous Chinese PhD graduate from the late 80s. And he said, well, in China, people don't know that CMU is so great in AI. They've heard of Stanford and Harvard, but not so much CMU. So why don't you do, this is going to be good for CMU. And I said, okay, we'll do it as an exhibition, not a scientific experiment per se. We'll do an exhibition because they didn't want to play as long. And my worry is that if we play some small number of hands, it's a coin flip. And that would be not good. So we played only 36,000 hands against 6 Chinese poker players. By the way, the brand that we used was not Libratus there. We used Lengfudashi, which was a name given to our AI by the Chinese team. I think it means Cold Poker Master. And these included China's one and only World Series of Poker bracelet winner. And these people had expertise in computer science and machine learning as well, not just poker. And when we got there, we kind of walked into a trap in that they had somehow scraped all of the hand history of the AI. So they had 120,000 hands of sample of how we play. We didn't know this in advance. Wasn't really explicitly forbidden, but anyway, so now we're facing a very different kind of opponent. And by the way, so when I got there, it's this 3-story building just for this event. There's this big media studio with professional poker commentators on one floor. There's the actual event on another floor. And then there's this one bottom floor where there's an elevator shaft and a door. So at one point I decided that I'm going to peek in there. And guess what I saw there? A long table of analysts on their computers doing real-time analysis of the play and giving the humans advice. That wasn't disallowed either, but I mean, this is what we were facing. All right. So now Lengfudashi won by 220 millibig blinds per game. So even more than we had won in January. And it also won each of the 9 sessions and beat each of the humans individually. So what does this say? Well, first of all, it says that the players we played in January were really good, in that they played better even without any background history on how we play. But the other thing is really more fundamental. It's really showing the power of game theory, as opposed to, say, reinforcement learning. In that the game theory approach is thinking about all possible strategies of the opponent. So it doesn't matter that they know our strategy. We're basically not exactly Nash, but approximately Nash. But an exact Nash equilibrium would be unbeatable even if they know exactly our strategy. And this is unlike what has been seen in RL approaches, like for Go and Dota 2. So if you've seen the Go documentary, even the European champion, who wasn't really the best in the world, was able to beat AlphaGo after some practice with it. And in Dota 2, even average humans can beat it once they get some practice with it. So this is a big lesson, I think. All right, and maybe there's something more general in this as well, to go on a limb a little bit. Maybe for adversarial machine learning, maybe there should be some more game theoretic thinking and so on. I know there's some initial connections already. All right, so how does Libratus work? Well, the high-level point is provably correct techniques. So you won't see, for example, deep learning here. These are all theoretically correct techniques. We were running on Bridges, which is the newest supercomputer at the Pittsburgh Supercomputing Center. We were running on CPUs back then. We also have GPU codes now. And in the end, time allowing, I'll talk about something that can be done on one server, which is not quite as good, but a newer technique. All right, so the architecture has really three main pieces. One is the pre-computation of what we call a blueprint strategy for the whole game. It takes on as input the rules of the game, runs an abstraction algorithm, and then runs an approximate equilibrium finding algorithm on the abstract game to come up with a blueprint strategy for both players for the whole game. Then there's a subgame solver, which takes the blueprint and solves the subgame that's actually reached to come up with a finer-grained strategy in a finer-grained abstraction. And now you might say, wait a second, Thomas, you just told me in the beginning that this is impossible, and now you're telling us that you're doing it. So what gives? I'm going to tell you how this is actually possible. The short answer is that the blueprint gives enough context that you can isolate the subgames in there enough that you can get probably correct techniques, even in these imperfect information games. And then there's a self-improvement module. And notice that this is not the typical way of using machine learning in games, which is opponent exploitation. Instead, I thought that would be very risky here, because we're playing against the best humans. They don't have very big holes to exploit, and they're world-leading experts at counter-exploitation. So let's not use those opponent exploitation techniques. Instead, we're doing a new kind of thing here, which is that we are letting the humans' actions tell us where the humans think that we have holes, and then overnight we are fixing those holes to play even more game theoretically in those spots. So that's nice in the sense that the patches are then universal. They apply against all opponents. And this is not a big data story. You could argue whether this is a machine learning story at all, but if you think about the first two modules, there's no data. It's a zero data story. You're just taking on the rules of the game as input. And here there's minimal machine learning, as I'll show you. So to put this in perspective, let's do a boxing analog. So if it's like shadow boxing against the mirror, and then jumping in the ring with Mike Tyson to see what happens. All right. So now let's go through these in order. So the abstraction works as follows. We have the rules of the game. The game tree is too big to represent, so we have the rules in compact form. We run a new abstraction algorithm. We get an abstracted game about 10 to the 14 or 10 to the 13. Then we run a new equilibrium finding algorithm to come up with an epsilon equilibrium for the abstracted game. This is about 50 terabytes of probabilities. And then you unabstract the answer to play the blueprint in the original game. The abstraction has two kinds of abstraction. One is chance abstraction, and the other is abstracting the player's actions. Chance abstraction in poker is abstracting the cards. We use the same algorithm that we used in Tartanian 8, which had won the annual, or baby version of which won the annual poker competition in 2016. But now in a much finer abstraction, and in particular for the first two betting rounds, we had no abstraction. So full understanding of the cards. And then in the latter two betting rounds, there's abstraction, but by the time we get there, the endgame solver kicks in, which doesn't have abstraction. So now we never play with card abstraction at any point in the game. Abstracting the player's actions, which is bet sizes in the case of poker. This is largely based on what top humans and top AIs from the past have done, but we also added radical bet sizes like big all-ins, tiny 10% bets. Why? Well, we just wanted to see whether it would ever play those with probability that's greater than 0. Might as well. And then we have this first convergent algorithm for finding optimal bet size combinations, but it's not very scalable. So we were using that only for the first two bet sizes. So we were optimizing the size of the first two bet sizes algorithmically. Now, what's a new equilibrium finding algorithm? Well, it's an improvement on Monte Carlo counterfactual regret minimization. Now, I'll unpack what that means. Some of you may already know that. Regret minimization is this technique where you are, based on your history, you're trying to minimize average regret. And counterfactual means that you don't do it in the space of strategies, but you do it at every information set separately. And you have to be careful how to glue those together. And Monte Carlo means that you're sampling. You're not traversing the whole game tree. Now, the new thing is that you start visiting less often paths where our own actions don't look promising. So where our own actions have very high negative regret currently. This gives you a speed up because you're visiting less often the bad paths, so we can solve larger abstractions. Also, in imperfect recall abstractions, which is a state-of-the-art abstraction, you have this issue that many different paths lead to the same abstract state in the future. And now, some of those paths will effectively get discounted away with this technique, so there's less fighting in those abstract states as to what you should do, because for different paths, how you got there, you might want to do different things. So you get actually better solution quality as well, not just better speed. All right, so now let's talk about subgame solving, and this is maybe the most novel part of the architecture. This is where we take the blueprint strategy and we compute a refined strategy in a finer-grained abstraction in the subgame that's reached during play. And if you think about the timing of this, think about this being weeks or months of computation in advance of the match. This like 30 or 40 seconds of computation during the hand, and this is an overnight process on, let's say, 200 servers. Okay, and now I'm going to jump into a little bit of detail here, so if you don't follow, it's okay. After 5 or 10 minutes, we'll get back to the high level. And I'm going to actually do a transformational analogy through the history of endgame solving in imperfect information games, because there have only been so few papers I can actually go through the whole thing. So, new ideas in the subgame solver, probably safe subgame solving, taking into account the opponent's mistakes in the hand so far. So let's talk about that first, and there I'm going to do the analogy. So the first techniques for subgame solving in imperfect information games were unsafe. That's what we call them nowadays. We didn't call it back then. So let's say that this is the blueprint strategy in this example coin toss game. It's not an exact equilibrium. Our equilibrium finder didn't give us an exact answer. So you can see it here, we're 50-50. Here we're quarter, 3/4. Here there's more heads guessing than tails guessing, and there's some forfeiting going on. So you can see that that's not really the best strategy, but it's a decent strategy. Then what we're trying to do, we're trying to compute a better strategy for Libratus as player 2. And here I'm going to show all of these techniques in the same abstraction, just for simplicity. In reality, we would want to change the abstraction so that we have a finer-grained game tree here under that player 2 information set. So the original idea of unsafe subgame solving is that we just use base rule. We assume that player 1 plays according to these probabilities from the blueprint, so then we get the probabilities here and here using base rule. And if you compute the best strategy to that, you'll see that player 2 would always guess heads. Okay, and that's a fine strategy if player 1 indeed sticks to that strategy up there, but it's of course highly exploitable in that player 1 could play so that's always a bad guess. Okay, so no theoretical guarantees, but this does well in practice in some domains. And it seems that in bigger domains, these type of problems are less prevalent, or at least less pronounced. Then the first safe subgame solving technique was called resolve refinement by Birch et al. Here, this is a little bit of a mind-bending thing, in that we are allowing the opponent to make an action which is a selection of abstractions. So here we have again the blueprint strategy in purple. And we can look at what's the expected value of playing in here, given player 2 strategy at 0. And here the expected value of playing is half. So now I'm going to construct this gadget game where I'm going to compute the player 2 strategy for the subgame as follows. I'm going to give player 1 the choice of entering the original abstraction and taking this expected value and this expected value, or I'm allowing player 1 to enter the subgame, which typically would be in a finer grained abstraction. So again, a little bit of a mind-bending thing. Now there's an action that we allow the opponent to take, which is not a real-world action. It's a selection between abstractions. All right. Now, player 1 can choose between entering the subgame or taking the expected value according to the blueprint of the subgame. What we want to make sure here in the gadget game is that the opponent's expected value of entering the subgame is no higher than in the blueprint. If we can guarantee that, then the strategy is probably no worse than the blueprint strategy. And in particular, if the blueprint was Nash, this is still Nash. Any questions on that idea? Okay. Now, trust me, here's what would come out, or one of the things that could come out of your solver, these purple numbers, and then you can see that they're the same numbers as here. So it might actually come up with the same strategy as the blueprint, so what have we actually accomplished? And then it might miss obvious opportunities for improvement, for example, never forfeiting. We know kind of intuitively that forfeiting is a bad idea. You might as well make a guess because it's free. So we know that this forfeiting is a mistake, and it's still there with positive probability. Okay, so the next improvement to that was called max margin refinement by Moravchik et al. Here we have again the same idea, choice of abstraction, so this is the same so far. It's similar to resolve, but punishes player 1 as much as possible for choosing entering rather than alt. So we define a margin for every type that the opponent might have. So in auctions it would be valuation types. Here it's heads or tails. So for example, the margin for heads is expected value of the alternative of heads minus the expected value of entering under heads. And we solve this by maximizing the minimum margin. This is in contrast to the previous slide where we simply attempt to make all of the margins non-negative. Yeah?
What does entering mean? Like,
Enter is the here. You're entering the
what does it-
subgame as opposed to choosing the blueprint.
but what do you do after you enter? Do you get a reward upon entering? Do you have to go all the way to the leaf of the tree to do you let the opponent choose your move?
We are trying to compute a strategy for player 2 here. And in this model, we are, well, let me show you that. So you would get 5 A's here, 3 A's here, 0 here. So there's no forfeiting anymore, and the expected value would be minus quarter here and a quarter here. And if you look at the margins, it's actually balancing the margin, so the margin here is the same as the margin here. Does it make sense now?
No.
No? Okay.
I still don't understand what is entering, because entering is a player 1 move, right?
Entering is a player 1 move. That is the choice of the abstraction. Player 1 can take the alternative here from the original blueprint abstraction or enter into this new subgame.
I see. You're just trying to maximize if he were to choose enter, in some sense.
We are trying to maximize how much he would lose by going enter instead of alt.
Yes. Okay.
Yeah, and here, how much he would lose is a quarter on here and a quarter here.
I see. So alt is kind of like, I don't want to play the game anymore. Let's stop here.
No, it's not that. It's not that I want to stop here. It's I want to play according to our original abstraction.
Okay. All right. That makes more sense. Okay.
Let me postpone the. We're running a little late here. Okay. So the newest then. Well, the problem here is that while we focus on reducing player 1's expected value for heads to minus quarter, player 1 can actually just sell for half in the head situation. So this is still somehow missing something. And the newest idea is what we call Reach-maxmargin refinement. And now we're solving a single subgame first. We'll talk about multiple in a second. Let's focus on this yellow part here. I'm not going to show you the gadget game, but here, somehow if player 1 plays here, player 1 is making a mistake of half, right? Player 1 is giving us a gift of half. So in the gadget game, we can increase the alternative payoff following heads by half, because choosing play would still be a mistake for player 1 there. So we can afford to give half, which is the size of the gift, back, and it would still be a mistake, or half minus epsilon. Thus, the gadget game solver focuses on reducing player 1's expected value for other types she may have. So that's the only extra thing over the previous slide, is that we're keeping track of these gifts, and we can afford for some types to give back something. And those are exactly the types where the gift was positive. For others, it was 0, and we can't afford to give back anything. So this gives us, in a way, a bigger polytype to optimize strategies over in a safe way. All right. So now 2 flies in the ointment, and this is kind of a side deal here, but one is that if multiple subgames are refined, the off-path expected values might not remain constant. So here, let's say that we have this same gift of half here. Now, we can, if we take the gift here, say that that's 1, this is half now. We can't also take, or we can take the gift here, but we can't take the gift on both sides on different subgame solves in different hands, because now we've made ourselves exploitable. So solution to this is we split the gifts among the subgames by the probability that the subgame is reached. So for example here, if this is half-half, we take half of the gift on this side and half of the gift on this side. There are other ways that are safe as well, but you can't count the full gift on all sides, because now you would no longer be safe. The other fly in the ointment is that the gifts might not be as large as we thought, because the subgames they come from will be improved. So let's say here, we thought the gift is half here, but because we're going to improve this subgame, the actual gift is only a quarter, and you can substitute the lower bound on the gift, and it can even be an estimate in practice. All right, oft reactions and nested subgame solving. Now this is going to be kind of mind-bending, that I can actually change the abstraction on the fly and still have Nash equilibrium guarantees. So normally, when the branching factor is large in games, like in No Limit Texas Hold'em, you actually just put some of the actions into the model. We call this action abstraction. And then we always can play into the abstraction because we control our actions. But the opponent might play something that's not in our model. So let's say the opponent plays that green action, then we pretend that they actually played the black action. And this is called the reverse mapping or action mapping. How do we map these green actions back into the abstraction? And there's a whole literature how to do that. The newest and latest and greatest on that strand is the HKI 13 paper, and we'll benchmark against that. Now, we want to get rid of that entirely. So what we do is that we are going to solve a subgame in real time, including the off-3 action that the opponent actually took. So now we're adding branches to our action abstraction or our game model on the fly, and we'd still like to be able to prove equilibrium properties. So here's what it would look like. So let's say that player 1 can take 3 actions with expected values x, y, and z, but instead, that's in our head, but in reality they do something else. So we actually construct this same kind of idea that player 1, the opponent, can actually choose between abstractions, either in the original game, where he gets the maximum of x, y, and z, the best of the original actions, or this new action, which is generated on the fly to be exactly the action that the opponent actually took. All right, so properties of this. This actually works even with hidden actions by chance, which you don't see in poker. So now let me define delta. This is not an assumption, it's a definition of delta. So let delta be such that there exists a Nash equilibrium where each alt payoff for player 1 is within delta of the Nash equilibrium expected value at that point for player 1. So that's basically saying, well, let me leave it at that. Then our Reach-maxmargin subgame solving technique yields a 2 delta minimax strategy for player 2 for the full game. So this means that we can actually change our abstraction on the fly, and we're still almost optimal. And how close to optimal we are is how off our blueprint was from Nash. If it was an exact Nash, we're still exact Nash. Now there's another version of this which talks about it in a different way, where if player 1's alt payoffs are computed from a best response in the full game to player 2's blueprint, then the strategy formed by our Reach-maxmargin subgame solving technique has no greater regret than for player 2 in the full game than player's 2 blueprint strategy. Saying that, okay, this is not going to make the blueprint, make the strategy worse than what it was. And notice that there's no notion of delta here. However bad your blueprint was, it's not going to get worse. Nested, this can actually be reapplied for every subsequent opponent of tree action as well. So we don't have to just do it once. We can apply the same over and over in the hand as we get deeper and deeper into the game. And theorem 1 prime is that now you're not off by 2 delta, you're 2 delta times number of reapplications within one playthrough. So if you're applying this 3 times, it's 6 delta. And theorem 2 prime for this setting, well, it's the same as 2. So you're not going to make the blueprint worse. All right, experiments on medium-sized games. This is not Texas Hold'em, because there you can't compute the best response to evaluate how exploitable you are. This is a medium-sized poker game. Our best reach subgame solving technique, there's actually multiple variations, has 3 times less exploitability than the best prior safe subgame solving technique. And the nested reach subgame solving is 12 times less exploitable than the best action mapping technique. So indeed, this idea of action mapping is dominated by this nested reach subgame solving. Okay. Also, the subgame solving starts much earlier. Typically, it had been 2 years by then only. It had been on the last betting round. Now we're actually starting it already on the 3rd betting round. There's no card abstraction in the subgame because we have these more scalable subgame solving techniques. And we can actually change our action abstraction between hands. Now that we're solving our subgames anew anyway, we might as well change our action abstraction a little bit. Because the value of the game is not very sensitive to the action abstraction, but the strategy is quite sensitive to it. This keeps our opponents on their toes all the time because they're facing a different action abstraction all the time, and they have to think through it every time. Okay, so now if you're a poker player, you know that this type of subgame solving would show up in what's known as blockers. How do you think about blocker cards? And if you don't know poker, don't worry about it. I'm going to play a video about the guy who's been interviewed is Daniel Macaulay. He's one of the 2 or 3 people in the world who has an open promise that they will play anybody in the world at this game. And notice, pay attention to what he says when he is called for an example. He has just played 30,000 hands of poker, and he's been asked to recall an example of a particular kind, and he just recalls it just like that.
You know, in contrast to the first challenge, there was a lot of hands the first time around where, you know, the bot really just punted one off. I've seen way less of that. So what are your thoughts? How good is the bot?
It's pretty good. I mean, well, I'm losing, so if I consider myself pretty good, then it must be pretty good. But there's not really any punting. Like, I think it uses blockers well in the bluff spots. Like, I've not really picked up on anything that's too obvious one way or the other. So like, I'm genuinely impressed. Yeah, it's pretty good.
Oh, okay. Maybe it's the next one where we see. Yeah, it's a later video where we see the example. All right. So let's talk about the last module, the self-improver. So again, I mentioned that we are not going to try to do opponent exploitation here, although there are algorithms for it. But it would be, in my opinion, it would have been too risky, so we didn't do it. We're going to instead do a different kind of idea that I think we're the first to do, where we let the opponent's actions tell us where the opponents think they've found holes in our strategy, and then we're going to fix those holes overnight to play more game theoretically in those spots. All right, so here's a simple example. So let's say Libratus moves first, then the opponent. This is our action abstraction in the blueprint. And let's say that the opponent has actually played also some of the actions out of the abstraction. So those green actions. Now we're going to automatically prioritize which of those are the biggest holes. And it has to do with how close you are to the prototypical actions, the blue ones, and how often they're played. The closer you are, the less of a problem it is, and the more often it's played, the bigger the problem it is. So let's say that this is the worst problem. We call this the top one hole. Now, we're going to generate a coarser card abstraction for that part, so we can solve it overnight instead of months. And we're going to put a default action, one of the already existing blue actions in there, even in an even coarser abstraction, so that we don't end up assuming that the opponent plays this with all possible cards that he might be here with. Then we're going to freeze this part of the blueprint strategy, and we're going to recompute this for epsilon equilibrium using the same algorithm overnight. And then we're going to throw this one away, and this gives us a strategy for a new branch of the game tree that wasn't there. All right, and we do this for the top K holes. Depending on how big your game is and how much supercomputing you have, you can do more or less holes. We typically try to do 2 or 3 holes a night, and then in the morning we had a test against our prior AIs to see whether the hole had been sufficiently solved, and if so, we would put it in the execution engine, and if not, then not. So now let's see what the humans say about the holes and the self-fixing of the holes.
The energy level was super high the first few days. You know, we start off in the hole, kind of expected as we're figuring out what's going on, and then we climbed all the way back to basically nearly even, and we are like, you know, we're in this, we have a chance. And we had like key strategy ideas, key things we were pushing against the AI. And then I guess the wheels kind of just came off the wagon, and it wasn't that our play fell apart, in my opinion. I think we've really seen a clear improvement in the AI strategy day to day to day.
Okay, and let's see what Jimmy Cho has to say about it.
The bot plays incredible. The first 2 or 3 nights, I severely underestimated its ability. I really thought that we were just going to find a couple simple leaks and just hammer away at it, and it'd just be a easy 20 days. But it's been the complete opposite. Every time we find something, it seems to adjust the next day, and we have to continue to look for leaks. But eventually, we're not able to find any.
Okay. Head strength of the top AIs. So higher on the slide is stronger. Here are ours on the left, others on the right. There are many other AIs. These are just showing the top ones. I guess the bottom line here is that usually you see an improvement of maybe 10 or 20 millibig blinds per game per year. And here we saw in 18 months, we saw 63 millibig blinds, which is a big improvement, mostly driven by the subgame solving. It didn't even measure the contribution of the last component. Another kind of interesting thing is that this Mordicum AI, which is our newest AI, which is not as strong as Libratus, but this was actually built just on one server. So this is not a supercomputing deal here at all. So observations about Libratus' play, well, strengths, it plays in an unusual way. So if you're looking for heterogeneity in AIs for games, this is what it's better to actually have at least one of the things be something that's generated from scratch rather than copying different humans, because humans always play in a kind of a subspace of the game, a strategy space. Small bets and huge all-ins plays a totally different kind of poker than humans had been used to. Multiple bet sizes in any one situation. Humans typically play 1 or at most 2. It plays these actions called limping and donk betting, which poker books universally say are bad. We do them regularly. Not all the time, but we do them with good probability. In all of the AIs, for example, that we've generated, limping happens with 8 to 12%. So that suggests that, it's not really a bad action. Perfect balance. Well, Nash would be perfect. Of course, we're not exact Nash, but that's what the humans called it. Mixed strategy. Probability distributions over players' hands, not just range-based thinking, which is really the supports of the distributions, as many pros do nowadays. Near-perfect subgame play, great use of blockers, different bet sizings used in different subgames. Weaknesses, well, there's no opponent exploitation, but that's by choice, in that we wanted to make something that's very hard to beat rather than something that would exploit weak players by the biggest possible amount. Now, over the 13, 14 years up to this point that I had been working on poker, I hadn't been a poker player, by the way, but I started to love the game over that time. And then when we finally got to this point, I started worrying, am I going to ruin the game? There's many ways to ruin a game. And one of them would be to say, okay, here's an optimal way of playing, and it's boring. So my worry was that we're going to find some sort of strategy that chisels a little bit of value here and there, and it's kind of boring. And let's see what Dong Kim, he's probably the #1 player in the world currently, has to say about that. Is safe play, equilibrium play in other words, is that timid or boring? And I apologize, there's some swearing in this video.
That a lot of people have asked me to ask you guys is, does the bot bluff?
The bot's kind of a nit.
Bot's a net?
The bot fucking bluffs. Or am I supposed to say that? Bot bluffs.
You can curse on YouTube.
Oh, okay, I didn't know that. Bot fucking bluffs. For sure. Gangster as fuck.
Confirm the bot does bluff.
Can you give me an example of maybe a crazy bot bluff that we wouldn't have seen from a person?
Today he flatted a 4-bet with 5-3 of clubs. The flop came King, Queen, Jack with 2 hearts. Check, check. I turn a flush. Check, check. Got to set the trap. 5 river, he bets. I raise small, he 3-bet jams.
That's a pretty gangster hand.
He's real gangster. Like, he's not messing around. And it's like manly bluffs, like big bets. Like, it's pretty gangster.
Yeah, you see, I think for humans in a lot of those situations, when it gets into weird lines, like a 4-bet pot, check, 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 and then all of a sudden there's bet raise 3-bet. I think a lot of players, they kind of are a little too afraid to maybe bluff. I think we can pretty safely say that is not the case here.
Yeah, it's like maybe a little bit afraid, and also just like everyone's range is so weird that it's really hard to choose which hands, whereas it can just like go this percentage of this hand or this percentage of that hand. So like in every situation you always question like what can it bluff with, and then you like realise it doesn't really matter, like it always has bluffs.
Okay, so I guess that answers your bluffing question to an extent at least. So now let me pop up back to a higher level and some current research on this topic in my lab. And I mean this topic as in game solving. We're doing other things like kidney exchange, advertising markets and things like that as well. But now I'll just focus on this. So one is lossy abstraction algorithms with bounds. So the abstraction algorithms that are currently used in practice, they don't have bounds on how much you lose, unless they're the lossless ones, but they don't abstract enough. The remaining game is still too big to solve. So now we have these lossy abstraction algorithms with bounds, and after we started developing those, I realized that they're not really about just abstraction for computational speed. They're also the same theory applies to looking at modeling. So all modeling is abstraction. And now this is talking about if we can measure the difference between reality, or bound the difference between reality and our model, then we can for the first time say that our game theoretic strategies have some bound on how good they are for the real world. Which is kind of astonishing in that we've been doing, game theorists have been doing game theory for many, many decades, yet there has been no discussion of how the answers that come out of models actually, how good are they for reality. Now, to do still is we need to unify our best practical abstraction algorithms with the theory. So the theoretical algorithms are not the same as the practically best ones currently. Simultaneous abstraction and equilibrium finding. So I showed you this waterfall, which is a traditional way of doing it, abstract first, then solve. Here we are actually allowing the equilibrium finder to tell what states are similar in their strategies, and therefore maybe they shouldn't be separated. And similarly, so there's an iteration between abstraction and equilibrium finding. And the key then is how do you actually warm start the equilibrium finder once you change your abstraction? Otherwise, it's way too slow. So we first had warm starting algorithms that relied on a particular kind of equilibrium finding algorithm. And now we can do general warm starts for CFR algorithms. So no matter where the initial strategies came from a different equilibrium finder, from human intuition, whatever, we can now start CFR with those. So you don't have to start from scratch. CFR is the counterfactual regret minimization. Then new fastest algorithm for the CFR family. So turns out that in the CFR family, CFR Plus has for a few years now been basically unbeatable. And a lot of people have tried to come up with new variants of the CFR family. And they've all been either way slower than CFR Plus or a little bit slower. But now we have something that's faster. As we're planning to submit within a month. Then regret decomposition framework. I mentioned that in CFR, you are actually decomposing the regret so that you can do regret minimization separately into information sets. But turns out that the way to do it in CFR is not the only way. There's actually this infinite family of exact decompositions you can do. And now you can go beyond the CFR family. And again, there you can get better algorithms than in the CFR framework. Then equilibrium finding algorithms by developing new theory of gradient-based techniques. So gradient-based techniques have better worst-case convergence rates than CFR by a lot. But in practice, CFR has been faster. It's kind of a mystery. And it's still kind of true, but now we're within a factor of 4 of CFR speed with these types of algorithms as well. Algorithms for equilibrium refinements. We talked about mostly Nash equilibrium today. But Nash equilibrium doesn't play optimally if the opponent or we have made a mistake in the game so far. And that's where equilibrium refinements come in. They're basically additional constraints on what counts as a good solution. And just to pick one here, this last one, trembling hand refinements are maybe the most famous family of those, and they have been very hard to compute, even for tiny games, and numerically unstable. So now we have algorithms that compute trembling hand refinements for games with about 10,000, maybe 30,000 nodes. So still way less scalable, but several orders of magnitude more scalable than before. Equilibrium finding algorithms for 2 agents, that's still way less scalable. We have the fastest one currently for normal form games, so matrix form games. And how it works is that we're doing tree search, not in the space of the discrete supports of the actions as to what actions are in play, like we and others have tried before, but in the space of the continuous probabilities. So we basically split the probability space into these hyperrectangles, and then we have an oracle which checks whether a hyperrectangle can potentially have an equilibrium in it in this nonlinear problem of more than 2 agents. And then exploration, exploitation versus exploitability. I've had this on this slide in my talks for a long time now, and we still haven't really cracked it, but I can say a few interesting things about it. So in reinforcement learning, there's this trade-off between exploration and exploitation. In games, there's also this third dimension of exploitability. As I start to exploit, how much do I open myself up to exploitation? And the folk wisdom had been that if I exploit more than any game theoretic strategy would, any Nash equilibrium strategy would, then I'm opening myself to exploitation. Turns out not true. You can actually completely safely exploit your opponent by more than that, up to a bound which we characterize. And it actually has a nice intuition in that I can't really, well, let me say what doesn't work first. So you might think that I can take the winnings that I have from Eric so far, and I can bankroll my exploitation. I can exploit him so much that I might lose up to what I've already won. Seems like that might be safe, but it's not safe because I'm mocking with my upside and my downside from an ex-ante perspective is still all there. So I need to be able to separate out what I have won based on luck versus Eric's mistakes. And if I can lower bound how much I've won based on Eric's mistakes, that is the amount that I can use to bankroll my exploitation in the future. And then a final thing on this slide is depth-limited solving in imperfect information games. So we talked about subgame solving, but that was solving the end of the game. Now we can actually solve the beginning and the middle as well on the fly. The idea that doesn't work here is to say, okay, I'm going to fix the opponent's strategy at the leaf to what they would play in the blueprint, because that gives me too much power. Instead, I'm going to give the opponent one final action at each leaf. It's each leaf information set. And there they can choose which strategy to play. And that takes away that extra power, and that is the idea based on which we can do depth-limited solving in imperfect information games. And this has theoretical guarantees, and this created the bot Modicum in my lab, which was created on one server, and to our knowledge, it's the second best AI for this problem. All right, so commercial applications, well, I think that most real-world settings are imperfect information games, although they're not treated as such. And now that we have this type of technology, I think we're going to start to see applications where things are really treated as games for what they are. So one example is strategic pricing. Typically, when companies do pricing, they optimize their prices, giving their competitors' prices fixed. Single agent problem. But in reality, of course, the competitors change their prices, and you don't want to be just re-optimizing to that and being reactive. You want to think about these things ahead. Same in strategic product portfolio optimization. Gaming, video games, training, streams. You can make really exciting streams by having these superhuman AIs play against each other. Bot detection. Turns out that they have moves that humans never play, and there are millions of them. And you can detect bots not just by looking at the operating system level, but really from the strategies themselves. Automated negotiation, electricity markets, various aspects of finance, investment banking, political campaigns, how do you spend media against an adversary, business strategy. Hey, wouldn't it be nice if there were actually some strategy in business strategy? Bidding, how do you bid, for example, for oil tracts, and then once you know how to bid, you can actually evaluate auction designs that you couldn't normally evaluate because you can't solve for equilibrium. Strategic market segmentation. Same thing as with pricing. Typically, market segmentation has been treated as a static problem. Of course, you have to think about strategically how would the competitors change their strategies in the future, change their segmentation in the future. Interaction between vehicles and autonomous fleets. So let's say that you have two operators of autonomous fleets in the future. The rules of the road put limits on what they can do, but there are a lot of unspecified things, like how do we merge, for example. Wouldn't it be nice if we wouldn't have to negotiate those in some ad hoc way on the fly, but there are too many negotiation situations to manually negotiate in advance, so you would want to somehow automate that. Acquisition strategy like movie rights. How should streaming companies buy movies? Which movies should they bid for? In what order should they buy them from the movie studios? What should they offer? And so on. Sports, of course. Lots of sports applications. And maybe the most radical, it's kind of a long story, but steering evolution and biological adaptation strategically. For example, for medical treatment planning or synthetic biology. And then there's a bunch of government applications. So if you think about it, traditionally, in military planning, whether it's cybersecurity or actual physical military or whatever, you assume a naive opponent, a naive red, a fixed strategy. You assign a strategy and then you simulate against that or do wargaming against that. Here, unlike simulation, red strategy is not input, but is rather output. So you're actually looking at all of the possible opponent strategies, and so you're robust. And that has a bunch of applications. Thank you very much.
Just out of curiosity, how do you wouldn't need your subgame innovations to do approximate good jobs in those open world messy spaces. It seems more of just in generically looking at game theoretic approaches in these spaces. Or have you seen actual application of the nuances of the way you solve the two-player poker game?
Yeah, so
as useful in the open world.
Yeah, so there's always a question of modeling. And when we think about business strategy for these two startups, we're looking at what are the closest, where we can say, okay, well, we have pretty good models. You start from there. Good models and close to zero sum or exactly zero sum. So you're really looking at very adversarial situations, high stakes, of course, and ones where the Rumsfeldian unknown unknowns are not that big big a deal. But no, modeling is really, I would say, the number one bottleneck here, is that if the real world is such that you can't really model it accurately, that is the number one showstopper. Now,
It's like a pretty big showstopper for most real-world applications.
well, I'm not sure. There's infinitely many real-world applications and probably infinitely many that you can model. So while it's a worry, I'm not really worried. And the other is the abstraction techniques. Now, if you can bound the difference between the real world and the model, you can say that, hey, even if you solve just the model, you're close to optimal for the real world.
Okay, open questions. Yeah, Paul.
So, part of the game theory approach is the idea that even if your opponent knows your policy right, it wouldn't change anything. But have you tried this with the humans in the sense that if you have a probability over a range of hands, then you can actually expose that to the humans because they still don't know what action you took, and actually start reflecting the internal state of the bot to them, right? So the bot would actually say, here's the hands I put you on. That's effectively a summary of the policy from the point of view of them. They don't know what action you took after that. Have you tried seeing that and see how they adapt or learn based on that?
No, but we've done something similar, and Eric and I were chatting a little bit about this on the fireside chat. So again, this comes to people believing in people. So we got into poker already before this event for the last few years before that, the last couple at least. It was a situation where when human expert poker players would tell us that, okay, the bot made a mistake. Chances were much higher that they were wrong than that the bot had made a mistake. And what we did, I had Chris Ferguson, who's a really kind of a mathematical PhD level guy, who's a top poker player, look at these situations where somebody told us that, hey, that was a mistake. Then we would give him the belief distributions and the path and everything. And he would actually write these little essays as to what happened. And every time, it was like superhuman reasoning in his words. It was thinking like 2 levels deeper than any human. And once he had 3 days to think about it, he would say that actually that was a brilliant move, not a mistake. But sometimes they look weird. Like one happened during the play. We had the AI called, I think maybe it was an all-in or some other huge pot, called a huge bet with Jack High. And most people who play poker would say, okay, well, that was a mistake. But turns out that exactly with that Jack and that other card, maybe it was a 3 or whatever, that is exactly with what you do. You play the light call just with that, because you have to light call with something, and with the blockers, that was exactly the hand to do the light call with. And you don't do it with 100%. You do it with some percent, which was not near 0. But once he really thought that through, he actually saw the merit in that.
What's your role of machine learning? Let's say, you talked about AlphaGo, and almost everyone here knows, the set of techniques that went into that, right? And now you have this really good, poker players. Is there any, does it help you, for example, in addition to that, you're solving it in a very strong manner, but does it help in compute, maybe the first part where you're doing the abstraction engine and it's many months or many thousand CPU cycles to try to learn from expert demonstrations and then do the compute upwards search seeded by that, or is that not still a viable strategy?
I see at least three roles. One is that we now have the warm start techniques. So you can actually warm start from any strategy, no matter how it's computed, whether it's computed with machine learning or some guy just thought that was a good idea. It doesn't matter. We can warm start from that. The second is that when we do opponent exploitation, those techniques, which we didn't use here, but those techniques, you could think of those as machine learning techniques which are kind of fortified by game theoretic reasoning. And there's definitely a role for machine learning and data. And then the third is the modeling. So I have to believe that machine learning, which is all backward looking, and strategic reasoning, which is all forward looking, they have to be somehow synergistic. And one of the ways that those are synergistic, I think, is that machine learning can be used to learn the model or aspects of the model. Like, for example, chance probabilities, which are not strategic, or what moves are possible, things like that.
have you tried putting the system yet in a tournament where, early rounds of tournaments are all about exploitation so that you can chip up and then have the chip advantage. How does it actually perform in sort of multiplayer situations?
Yeah, this one, we haven't really played tournaments and we haven't played multiplayer. We have a couple of early papers a long time ago on 3-player jam fall tournaments, like 3-player endgames of tournaments. But we haven't really looked at tournament play per se. One thing I can say is that when it comes to not tournaments but multiplayer, I hear from a lot of botters, not academics but botters, that the way they generate the top bots today for, let's say, 6max, they're very much the same techniques. So while in theory there's this big complexity gap between 2-player zero-sum games and more general games, in practice, at least for poker, it seems that the same techniques do well even in those more general settings. Yeah.
So your original blueprint is over some abstraction, but it's Nash, right? Is that somewhat?
It's an approximate Nash for some abstraction, yes.
And so even in that, I guess for any coarse or fine abstraction, at least in poker, it seems that once you have a good model, the right move is kind of, I wouldn't say immediate, but at least computable, right? You could say this is the right move distribution. But I guess in real life, even if I know the right move is to exit the room, it takes a lot of actuator to actually affect that goal, right? So like, I guess there are settings where you have the goal, but it takes some extra mileage to actually reach that goal, right? And I think in poker it's more immediate, right? I need to make this move and you could directly affect that move, right? But I think, how do you reason about that? Where even if the model of the world is taken, to reach some goal, there needs to be some kind of planning or learning how to actually perform the action that do it, right? It's kind of like, I know the best thing to do is if I take my 3-point shot here, but I can't do it because I cannot make the shot. Or like, how do you reason about that?
Yeah, well, we don't. You're right, we don't. When we take an action, it's not like robotics where there's slippage and whatever. It's like when we take an action, that action happens. Yes. But I'll take issue with the first part, which is that somehow when you get the abstraction, it's somehow immediate what the probabilities should be. That's very hard to compute with algorithms that have been developed over 14, 15 years on a supercomputer for months. So it's not immediate.
It's computable, right? So is there, I mean, there will be cases where these is, no matter how much you compute, it's not computable, right? Like how do you reason about that?
Yeah, I'm personally not that interested in that question, but yeah, I can tell you some things that people have done. So there's, for example, game theoretic strategies under execution uncertainty. There are a few papers on that. Mm-hmm. For example, for billiards.
I see.
But not from my group. But.
Okay. Thank you.
So let's stop there. Thank you.
Thank you.